paper 2 on diffraction gratings and that kind of stuff. So first part there, for some reason this question has got a biologist in it. Don't know what that's about. But explain briefly how a diffraction grating produces a continuous spectrum from the ray of sunlight. Now the answer to this is quite lengthy, so I won't bother writing it down. Switched it off. So the diffraction grating diffracts the different wavelengths of white light, which is basically what gives you this spectrum. Red light is diffracted the most, violet is refracted the least. At position X on the screen here, violet light waves have interfered constructively to produce a band of violet. So we can see the light, so it must be constructive interference. So all the violet light has interfered constructively to produce a bright band. At point Y, the red light has interfered constructively to produce a bright band of red light, and the same goes for all the colours in between. So it's basically a continuous spectrum is produced because you've got different wavelengths of light. Different wavelengths of light diffract differently through the diffraction grating. They interfere constructively on the screen to produce a spectrum. Okay. B, part 1. This is where we get to the calculation. The wavelength of the light at the end X of the spectrum is 410 nanometers. Calculate the angle theta. So you know it's a maxima, you know it's something you can see, it's a bright patch or an area of constructive interference. So it's n lambda equals d sine theta. Now you need to figure out first of all what d is. You know how many lines per meter there are, so it's a wee bit easier than some of the examples we've looked at. D is equal to 1 over 6 times 10 to the 5, which is 1.67 times 10 to the negative 6 meters. That's the separation of just two slits. That's the gap between two of the slits. So it's the first order spectrum that we're looking at. So n is 1. The wavelength is 410 times 10 to the negative 9. D we've just figured out as 1.67 times 10 to the negative 6. And sine theta is what we are trying to figure out. So sine theta ends up being 410 times 10 to the negative 9 divided by 1.67 times 10 to the negative 6. 0.246. Theta is 14.2 degrees. Part 2. Let's do part 2 up here. The angle A in the diagram above is 9 degrees. Calculate the wavelength at the end Y of the spectrum. Well, you've got 9 degrees in here, 9 degrees in here, and you already know that this is 14.2. So the angle of deviation from the normal for the light at Y is going to be 14.2 plus 9 degrees. So that's sine theta in this case. So 23.2 degrees. You can then use the same equation as before. N lambda equals d sine theta, which is your equation for a diffraction grating with a maxima. So lambda is 1.67, this is still 1, even though it's a different colour, times 10 to the 6. 10 to the negative 6 times sine 32, 23.2. Lambda is 6.6 times 10 to the negative 7 meters, or in other words 660 nanometers. Okay, so it's applying the same equation twice. It's just making sure that you understand really that this angle is the angle of deviation to whatever area of constructive interference you're thinking about. C, the biologist. now uses a triangular glass prism to produce a continuous spectrum from a ray of sunlight. State two differences between this spectrum and the spectrum produced on the grating. So we've done both these experiments. The easiest ones to remember are that they are in a prism, the blue light is refracted the most, whereas in a diffraction grating, red is diffracted the most. So it's the biggest change of direction for red in a diffraction grating, smallest change of direction for red in a prism. The other thing is that a diffraction grating produces several of these, several spectra, whereas a prism only produces one. Another thing you could say is that the diffraction grating produces a central band of white light, which the prism obviously does not. There's three differences for you. Any two of those will get you your full 2 marks.